When we deal with the binary search tree, okay, the main function is search. It means we are going to search the key, and we need to find how to search the key in the correct way. So to search for a key K, we trace a downward path starting at the root. So this is the root. Okay, we call it, this is the root. And as you know, this is the internal node. And this is the external node. So the next node visited depends on the comparison of K with the key of the current node. So comparison. So it means I need to compare whether the key is lower or higher than the K. If we reach a leaf, then the key is not found. So let's say I want to find 4. Then I'm going to call the function search, the tree search 4, root. It means I'm going to search number 4, and the starting will be from the root. So the tree is T, and then I'm going to search the P, which is the value 4, and then the K. K means the key that you are now starting on. So let's say if the key K is the root, we have the key K is the root, then 4. Check. If K equals to the P dot key, so I'm going to check if the K here is the key, 6. 6 is the 4 equals to 6. 6. Okay, because 4 is not equal to 6, then let's go to this one. K is less than P dot key. So K, K is the root. Then 6 is less than P dot key. So 6 is less than 4. And P dot left P is not known. So P is the key here. Yeah, it is not known. Then if 6 less than, or maybe the K here is, or maybe this is the opposite. So the idea is if we have the 4, 4 is less than 6. If 4 is less than 6, then we go to the left and check. If the left is not known, then we go to the tree search again. Then this is recursion. We go to the left. Now we know that the key is 2. So 4 equals to 2. No. And then check. 4 is less than 2. No. Then 4 is higher than 2. Yes. And check. The right P is not known. The right P is not known. Yes, it is not known. Then we go recursion. So we go recursion to the tree search. And then now we go to this section. Now let's check. 4 is equal to 4. Yes, because 4 equals to 4, then return P. So return what you already look at this internal node. So this algorithm for the nearest neighbor queries are similar. So we want to find what is the nearest from the key. How if we want to insert? How if we want to insert a value? So to perform the operation put k comma o, we want to put the k of an object o. So we need to search the key k. The key k. First, we will search using the tree search. Let's assume k is not already in the tree, because if you use the same number, let's say I want to insert 6, but 6 is already here, so there will be another function. Okay, so let's assume that k is not in the tree, and let w be the none. What is none? None means this one, this one, this one. So none is the external node. None is the leaf reached by the search. So we want to insert k at node w and expand w into an internal node. So we call this is w. Yeah, this is w, 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 w. And then we want to put this w into an internal node. So we choose 1. After we choose 1, then we put it as an internal node. For example, I want to insert 5. Then I need to check 5 from the root. 5 is less than 6. Yes, then it goes to the left. And then we compare with 2. 5 is less than 2. No. Then check. 5 is higher than 2. Yes. Then we go to the right. 5 is less than 4. No. 5 is higher than 4. Yes. Then we go to the right. Then this is the external node. Okay. So this is the external node that we want to use to insert 5. Then 5 will be here. So this is the new node of 5. And W here will add a new external node. So there will be 2 external nodes, and this is node, and this is also another node. This is node, and this is node. Then the new tree will be like this one. We use the tree insert. This is the insertion function. Tree insert t on the tree k comma v. Okay, so I want to insert k with the value v. So search first. After we search, then check. If the k equals to the key, then yeah, you can set the p equals to v. If you cannot find, yeah, then check the left and add the node with the item key, the k comma v as the left child of p. Otherwise, yeah, select the node in the right child of the P. Now, how if we want to remove or delete? So in order to perform the removal, we search for the key K. Assume that the K is in the tree. Okay. So let's now just find some key that available in the tree. Okay. And then let V be the node storing key. So we have the V, yeah, but we do not use the value. Okay, let's just V is the node, the store the key. If the node V has none, leave child W. What does it mean by none? None is this one. None. This is the external node. This is the node. If the node V has none, we remove V and W from the tree with operation remove external W. So we remove the external node and we remove the W and its parent. So for example, I want to remove 4. So again, I will check 4 from the root. 4 is less than 6. Yes. Then we go to the left. 4 is less than 2. No. And then check. 4 is higher than 2. Yes. Then it goes to the right. Okay. 4 equals to 4. Yes. So I'm going to remove 4. And 4, it has one external node. Then we remove this external node and we lift up the node 5. Now it connects to the node 2. Now, let's consider another kind of situation. We consider the case where the key K to be removed is stored at the node V whose children are both internal. So for example, I want to remove 3. 3, in this case, this is internal node and this is internal node. So how can we remove this node? At first, we need to find the internal node W that follows V in an in-order traversal. What is in-order traversal? The in-order traversal means I will follow the sequence based on the sorted key. Okay. We copy the key W into the V, and then we remove W and its left child Z, which must be a leaf, by means operation of remove external Z. So for example, I want to remove 3. Okay. So when I want to remove 3, so I will check from the root. Okay. 3 equals to 1. No. And 3 is less than 1. No. 3 is higher than 1. Yes. Okay, we go to the right. So 3 equals to 3. Yes. Then we will remove this 3. Once we want to remove this 3, what happened? To the next is we need to find what would be the best to replace V. If 2 is here, what happened? So if 2 is here, then it will go to the directly the external node. We cannot do that one because it is the internal node. So we need to find another internal node. Okay. We need to find internal node that follows V in an in-order traversal. So after 3, what is the next node? Is 5. Okay, we follow the in-order traversal. Then after 3, we select 5. Then we copy the key W. So we copy the 5 into the node V. So we copy 5 into this position. And then we remove W. So we remove here. And then the left child here is the node. We also remove it by means the operation remove the external. So we remove the external and then we remove the external. Now we can see that 5 will be here and it follows the rule that the left child should be less than this internal node and the right child should be higher than this internal node. So this is the deletion when both of them are internal nodes. So the performance that we can look at for the binary search tree. Okay. So at least we have 3 kind of functions. Okay. Search function, we have insert function, and we have delete function. Yeah. For every algorithm that you created, so when you create your algorithm for the final project, I will check this one. What is your search function? And then how to insert and how to delete your elements or your items in your data. So here the performance is consider an order map with n items implemented by means of a binary search tree of head H. So the head is this one. This is the head. And this is the head. The space is ON. Okay, we have 1, 2, 3, 4, 5. Then the space will be n times. And 1, 2, 3, 4, 5, 6, 7. So it means the space will be n times. The search and update methods take OH time. OH means it follows with the head of the tree. If the head is 1, 2, 3, 4, then it follows with the head. If the head is 2, then it follows with the head. Because as you know, the binary tree, is a tree with at most 2 nodes, left and right, left and right, left and right, left and right, left and right. So this is also a kind of binary tree. So the search and the update methods can take OH time. So the head is ON in the worst case. So if we have like this one, we have 1, 2, 3, 4. Okay. So if we have 4 like this one, then it means in the worst case it will be like ON. So not exactly on, but yeah, it is approximately n. Yeah, that's why we call it on. But in the best case, we can have O log n. O log n is this one. We have 1, 2, 3, 4, 5, 6, 7. Okay. So the performance is about log 7. So log 7, it is about 2 something something. So it is approximately is 2. Okay. This is the implementation of the tree map. Okay. If you look at this one, it used the position. Okay. If you still remember, before the mid exam, we learned about the position list. Okay. In the position list, we have the position for every of our data. The position means the key, and we have the value. And we can do the search. Okay, so this is the search. And then we can check what is the first position, and we can check what is the last position. Okay, the first means I want to check the first, the last, I want to check the last, before. So I want to check what is the element before one of this position. And then I want to check what is the element after one position. So this is the way that I mentioned to you in the animation before. Find the minimum. Okay. So you can find the minimum key. Okay. So the minimum key, if you have the 3, something like this one, the minimum key will be the most left node. Okay. Find greater than or equal to. As I mentioned to you before, find GE. Okay. Find GE means we want to find a value key which is greater than a particular value. Or we can find the range, start and stop. So start is a particular condition of starting node, and then stop is the particular node for the stopping criteria. The other is just to get items. I want to get what is the value of k, set the value for a particular k, and then this is the iteration. So I'm going to do the loop. And then I can remove the key. So the one that I mentioned to you before, how to remove the key. So I want to remove in a particular position. First, we need to validate and then check whether it is on the left or it has on the right. So if it has 2 children, then it means it is it has 2 children, so it has 2 internal nodes. Then we will do this replacement. If not, then it is just removing the key. This is the delete item. So that's all about the chapter on the week 9. So last week we cannot complete this one. Now let's move to the next section. It is about the sorting. So in the sorting, we will learn at least 3 things. First is the priority queue. What is priority queue? And then we will learn 2 methods for the sorting, which is merge sort and queue sort. Priority queue. We call priority queue ADT. It is a priority queue, stores a collection of items and it is using the map. It is using the map. If you still remember the map, it is a pair of key and value. Okay, we have key and value. And the main method of the priority queue is to add k comma x. So insert an item with key k and the value x, and we can remove the minimum, or remove and return the item with the smallest key. So the additional methods, we can find what is the minimum values. Okay. So I want to return, but to not remove it, item with the smallest key. And then I want to know how many items do I have in this priority queue. And it checks whether it is empty or not. If it is true, then if it is empty. If it is false, it is not empty. So the application can be anything. Okay. So for example, the flyers. So when you deliver the flyers, you will deliver from the upside. Or auctions mean whenever you want to sell an item, when you want to sell a product, then you will ask the user, what is your price? Okay, my price is 5,000 won. Okay, if someone give a higher price, 6,000 won, then he will be the priority. And then someone put another price, 6,500. Okay, then this person will be the more priority. Someone put the price 10,000. Okay, this will be more priority, and so on. So that's why we call it, this is priority. Stock markets. So if you know the stock markets, it also have the kind of sorting. So who is in the top, who is on the second, who is on the third, and so on. So we want to set who is the priority stock market in these days, and so on. So the priority queue, it follows like this one. Let's suppose I have the empty dictionary at the first. So this is empty. And then I'm going to add 5 comma A. So I'm going to add 5, which is a key, and then A, it is the item. Then in the first priority queue, I have 5 comma A. And then I'm going to add 9 comma C. So I have 5 comma A. And then I need to check 9 comma C. 5 and 9. Where is the position? Okay, I know that 9 is higher than 5. So I put 9 after 5. Now I'm going to add another items, 3 comma B. So I need to check 3. Let's check 3 with 5. Okay, 3 with 5. I know that 3 is less than 5. So I put 3 before 5. I want to add 7 comma D. So I need to check 7 is less than 3. No. 7 is less than 5. No. 7 is less than 9. Yes. Then I put 7 before 9 and after 5. So I can check what is the minimum. The minimum will be 3. And then I want to remove the minimum. So I remove 3B. I want to remove the minimum. The next minimum is 5A. Now I want to know how many items do I have, because there are 2, so it will show 2. Now I want to remove the minimum, so 7 will be removed. I want to remove the minimum, so 9 will be removed. I want to check if it is empty or not. Yes, this is empty, so it is true. And then let's say I want to remove the minimum. It becomes error because it is already empty. So it follows with the total order relations. So the one that I already explained before. The idea of the priority queue also use the total order relation. So the key in the priority queue can be arbitrary objects. What is arbitrary objects? It can be anything. Maybe it can be string, can be number, and so on. And if it is an arbitrary object, we can do the ordering, or we can do the sorting. So if it is a string, then yeah, you can use like hash function. You can use hash function to do the transformation from the string into integer. After you transform the string into integer, then you can do the ordering, or you can do the sorting. So two distinct entries in the priority queue can have the same key. Okay. So the same key can happen in the priority queue. So the mathematical concept for the total order relation, I think you still remember, we have the reflexive properties. The reflexive property means x is equal then less than x. Anti-symmetric properties, it means x is less than y and y is less than or equal to x, then it means x equal to y. And the transitive properties means the x less than or equal to y and y less than or equal to z. It means that x equal less than or equal to z. In the priority queue, okay, we have the item. Again, we are using the map. So the map is a key value pair. Okay. So an item here, it means we have the key and value. So we have key and value when we construct as a priority queue. So priority queue store items to allow the efficient insertion and removal based on the keys. So when we insert the key, okay, so we can check the LT. LT means less than. So we want to check the key whether it is less than the other key or not. Okay, if empty, it means I want to check whether the priority queue is empty or not. So there are two kinds of priority queue. Okay. So we have the sequence-based priority queue. If we implement with an unsorted list, it means when we have a value 4, and then we put another value 5, and then we put another value 2, and then we put another value 3, and then we put another value 1. So we will put the new value at the end of the list. When we put this new item at the end of the list, it means we do the add operation with O1 time, because every time we have a new value, we put at the end of the list, at the end of the list, at the end of the list. since we can insert the item at the beginning or at the end of the sequence. But when we want to remove the minimum, or if we want to find the minimum, what is it? When we want to find the minimum, it means, okay, this is the minimum. Then it will take on time. Since we have to traverse the entire sequence to find the smallest key. So I have to check, is it the minimum? No. 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 Is it the minimum? Yes. So at least we need to take on for finding the minimum. However, we can do with the sorted list. Sorted list means after I have 4, okay, and then I have another value 5. So I will check 4 and 5. Where is first? Okay, then 4 is first, then 5. And then I check 2. So I need to check 2 compared to 4. Is it lower than 4? Yes. Okay, then 2. Is it lower than 5? Yes. Then I will have a new sequence. This is 2, 4, and 5. And then I have new item 3. So I will check 2 is less than 3? No. 2 is less than 3? Yes. Okay. 4 is less than 3? No. Then, okay, 2 will be placed before 4. So we call this is the sorted list. We will sort during the add operation. So if we add the items, we will do checking at least for n times. Since we have to find the place where to insert the item. After we know that the item is in between 2 and 4, okay, then we put 3. Okay. So that's why it will be like n times. And the remove min or finding the minimum value, it will take one time, because I already know that the minimum will be always at the front. Since the smallest key is at the beginning, so I always know that the beginning is always the minimum key. Now, which one is better? Using unsorted list or using sorted list? So this is unsorted list implementation. When you are using the unsorted priority queue, we have the find minimum. The find minimum means, yeah, we are using the loop. So we are looking the smallest element throughout the priority queue. The constructor, it is just to make a new instance. The length, it is to find the length. Add means I'm just adding the value into the last element. And then minimum. So I want to find the minimum. Finding the minimum means we use this method. So this is n times, or yeah, on. And to remove the minimum, yeah, this is also finding the minimum. So it means it will take on. Yes. If we are using the sorted list, it means the init is the constructor. We just create a new instance. I want to check how many items do I have. And then when I add the data, I will check where is the good position of this data. So the good position of this data means I will check for every possibility whether this key is minimum or not. So this will be on. So the add function will be n times. To find the minimum, we just need to find the first. The first will be the minimum. And to remove the minimum, we also need to get the first data. Okay. Then this is will give you O1. So both of them have the benefit. Whether you want to add with the n times and find the minimum with O1, or you want to add with O1 and find the minimum with n times. So there are two options for this kind of implementation. So we go to the sorting. So the sorting element means, yeah, we can use the priority queue to sort a set of comparable elements. So insert the elements one by one with a series of add operations. And then remove the elements in sorted order with a series of remove min operation. So if you are using the priority queue sort, means I want to make the input as a sequence and then make a comparator C. And the sequence, the output will be the S with the increasing order according to the comparator. So the running time of this sorting method depends on the priority queue implementation. So the priority queue implementation, whether you are using the unsorting list or you are using the sorting list. If you are using the unsorted list or unsorting list, it means you will do the add at the end. And then when you do the minimum or find the minimum, then you will do the sorting. If you do with the sort list, means you do the add with the sort and then just find the minimum, which is the first position of your list. So using the priority queue sort means that, yeah, we are placing the P, which is the priority queue with the comparator C. So if S is not empty, then remove the first. And then P at the E until it is empty. Okay. So when P is not empty, then remove the minimum with the key. And then add in the last of the S. There are selection sort. It means that we want to select what is the element that we want to sort. Okay. The selection sort is the variation of priority queue sort, where the priority queue is implemented with unsorted sequence. So unsorted sequence means this is the same with the unsorted list. This unsorted list means when you add 4 and then 5 and then 1 and then 3 and then 2. So you add at the end of the list. If you are doing with the selection sort, inserting the elements into the priority queue with an insert operation will take O(n) times. So if you do, this is the list, and then you put into the priority queue. When you put those elements into the priority queue, if we have n elements, of course, it will be n times. Removing the elements in the sorted orders from the priority queue with n remove min operation will take proportionally n times. So after we do this transfer into the priority queue, and then we sort this element. Sorting this element, finding the minimum, removing, finding the minimum from the n elements. So we have 1, and then 2, and then 3, and then 4, and then 5. It will take another n times. So the selection sort will run for n times, transferring to the priority queue. After transferring to the priority queue, we will do the sorting another n time. Then we have n power of 2. So this is the example. I have the input 7, 4, 8, 2, 5, 3, 9. So this is the sequence. In the first phase, we will remove this sequence into the priority queue. So I will select from the order. So 7, and then 4, and then 8, and then 2, and then 5, and then 9, and then 3, and then 9. So it will take n times. Okay, so this will be O n times in order to remove from sequence S into the priority queue. After I have this one, then in the phase 2, I have this priority queue. I need to sort. Okay, I need to sort from this one. Sorting means I need to find the minimum. What is the minimum from this one? This is not, this is not, this is not. Okay, this is the minimum. So I'll know this is the minimum, then I will move 2 into the sequence. So after I remove this one, then the remaining will be 7, 4, 8, 5, 3, and 9. And then find the minimum. So the minimum will be 3. So 3 will be inserted into the sequence. So the remaining will be 7, 4, 8, 5, and 9. Find the minimum. The minimum is 4. Then 4 will be added to here. And the remaining will be 7, 8, 5, and 9. 5 is the minimum. So 5 will be inserted into sequence. So now the remaining is 7, 8, and 9. The minimum is 7. Then we go here. Then we have the remaining 8 and 9. 8 will be the minimum. It's just here. And 9, the last one, is here. So at the end, we have this sequence. If we do with the insertion sort, okay, we call it insertion sort. It is the variation of the priority sort where the priority queue is implemented with sorted sequence. Okay. So the sorted sequence, this is the same with the sorted list. The sorted list, we again using the insertion sort. When we insert the element into the priority queue, we have n insert operation that takes proportionally until n times. And then when we remove the elements in the sorted order from the priority queue, it will take another n operation. So it will take n times. So the insertion sort, it will be n power of 2. So the idea is this one. The sequence, I have 7, 4, 8, 2, 5, 3, 9. Okay. So I will do removal from the first element, 7. Okay. And then I remove 4. But when I remove 4, I need to check where is the position of 4. 4 is less than 7 or 4 is higher than 7? 4 is less than 7. Then I will put 4 before 7. And then I will remove 8. What is 8? 8. Is it less than 4 or is it higher than 4? Is it higher than 4? Then let's check with 7. 8 is less than 7 or higher than 7? Is it higher? It is higher than 7. Then we put 8. And then we remove 2. 2 again we check with 4. 2 is less than 4? Yes. Okay, then we put 2 at the beginning. We remove 5. 5 we check with 2. 5 is less than 2? No. And then go next. 5 is less than 4? No. And then check. 5 is less than 7? Yes. Then we put 5 before 7. And so on. So we have this as a priority queue in already sorted. After we have this sorted sequence, then we just remove it into the sequence. So we remove the minimum, we remove the minimum, we remove the minimum, we remove the minimum, and yeah, this will be for n times. This also n times. That's why in total we have O(n) power of 2. For the last one, it is the in-place insertion sort. So it is just to swap. Okay. Instead of using the external data structure, we call the external data structure is using the priority queue. So we can implement the selection sort and insertion sort in place. In place means a portion of the input sequence itself serves as the priority queue. So if we have 5, 4, 2, 3, 1, okay, we can in place. In place means we just use the position. Okay. So we keep sorted the initial portion of the sequence and then swap. Swap means we want to find 5 and 4. Which one is lower? Okay, 4 is lower than 5. Then swap. Then already 4 and 5. Now let's check with 2. Okay. 5 compare with 2. Okay, 2 is lower than 5. Then swap. And then now 4 and 2. So 2 is less than 4. Then swap. So now we have 2, 4, and 5. Again, we will check with 3. 3 and 5. 3 is less than 5? Yes, then swap. So here is 3. 3 is less than 4? Yes, then swap. 3 and 2. 3 is less than 2? No. Again, 5 is less, 1 is less than 5? Yes, then swap. Then 1. 1 is less than 4? Yes, swap. 1 is less than 3? Yes, swap. 1 is less than 2? Yes, swap. Then we have the full sorted like this one. 1, 2, 3, 4, 5. So we call this is using the swapping function. Okay, let me stop here. Let's have a break. I will continue after the break.